so somehow this talk is very like as a talk. I'm gonna, we are all as quantum topologists. Someone gives you a possibility of a quantum group, and then you get an invariant, and then try to figure out what the topology of this invariant is talking about and what's going on. And somehow we are doing that for some time now, and I'm not sure how successful we are, but we have some success. But now what I'm proposing in this talk is going the other way. I'm going to tell you a construction that I'll give you a topological object, maybe not a link, and I will give you back a representation. And then one kind of question you can ask, okay, what is interpretation, or was it organized, is it complicated, how is it behave? So everything is coming from homology. So I will recall pass, so many. So there's a pass from constitutional topology that we all know. I will repeat it very quickly. And then most of the talk I'm going to talk about there's a pass from topology to quantum theory. So I want to discuss. So all of this I'm saying today is joint work with you, Susan and Robert. And well, probably one of the first time in my life I can state a theorem right at the beginning, which is the following one. But also because most of you may know at least all work. So the equivariant Kohanov-Lozansky link homology can be understood with an SL2 action, just to make clear which is invariant, meaning that we upgrade the usual bigraded link homology, which is just a vector space or a module, whatever you want it, with an additional structure, which is a structure of a SL2 representation. And moreover, I don't want to be too precise with this part, but this is the fun part. Moreover, this action is functorial. Well, in proportions. I will hope to say more about at the end of the talk. So ideally, you would like to say, I have a functor from links, category of links, objects are links, morphism of embedded surface in the 4 space, which associate to a link an SL2 representation and to a surface SL2 representation morphism. This is slightly more tricky than that. If you like this statement is true if your morphism is if your surface is a concordance. So if your surface has no topology, so it's just a cylinder, then the statement I just said is true. In general, you have just to take care a bit more about the topology of the surface. That you have to modify a bit the SL2 action properly at the source of the target such that the statement becomes true. So I like to think about something pretty tricky. And I made, okay, that's the goal. I want to discuss this theorem. I mean, how much I can tell about our theorem. So let's fix the SL2 in the statement. So just to make clear, we are clear about the definition. So SL2, see it's generated by E, F, and H with your usual relation. HE is 2E, HF is 2F, and commutator of E
minus 12
H.
Minus 12.
Sorry?
Maybe minus 12. It's
negative.
negative.
Okay, so that's one thing. And now I would like to consider an example of an application which is somehow very central. So I pick, let's say, M. Z of x1 xn, so the polynomial variable, so the polynomial ring is n variables. Good. And then you can act with E with this formula minus the sum of the partial derivative of xi from I equal 1 to n. F acts with minus x squared xi squared partial derivative of xi, and the action of H is just sum of the xi partial derivative of xi from I equal 1 to n, and I forget the sum here. Okay, you can check that. This is a necessary opposition. I don't know how common it is, but I mean, it's easy to check it is. And one remark is that the submodel of the symmetric polynomials is obviously stable by this action.
So which representation is it?
Sorry?
Which representation, sorry?
This is a necessary opposition.
Yeah, which one? So, I mean, we
Which
know
weights?
they're classified.
It's a bunch of Murmur. Yes, that's a good answer.
That's a problem for us.
Okay, this is what I want. Yeah.
I mean, if this one is just a tensor product of Murmurs, and this one is slightly more tricky to handle, but I mean, not that much. But I mean, mostly the first thing is that, of course, it's infinite dimensional. It's not a priori in category O. So it's not like a nice essential representation or the one I learned when I learned about quantum topology. But nevertheless, it's an essential representation. All good?
It's in category.
Normal.
It's some of your mass, right? It's category.
It's not a product of.
Unless n equal 1, it's not.
Sorry?
Unless n equal 1, it's not.
Less n equal 1 is not.
But still tensor product, right? It will be infinite direct sum of Verma modules.
It's not that bad.
In completion of a category O.
It's in reasonable completion of categories that people work with in some situation. I mean, but strictly speaking, it's not. It's in the usual definition of category O because. Good. So far, so good. Probably, yeah. So. Link homology, so I forget the word here, sorry. GLN, link homology, and is great record. Okay, good. Let's think a second. Let's consider the end nuts. So, and for simplicity, I will just consider the usual Corona homology. So just, we call you Corona homology of the N naught is just Z of X. I will take this one, E1, E2, modded out by x squared minus E1 x plus E2. Okay, and what else I want to say is that, of course, the claim is that there is an action of E, F, and H of that. I already told you what the action of E1 and E2 is. And like, obviously, if you want to do that, you're going to extend the action of E, F, and H basically by adding x dx, or x squared dx squared, or dx generally. And the only thing you have to check that this would obviously make this idea stable by the action, so you can mod out by it, and you got an SR2 computation as well. Is that okay, or do I put the details? So I mean, you just take the formula and add x to the story, and the idea will be stable. And so that's the Covana homology of the N naught. I should say that this talk I will ignore all questions about grading.
Yeah, I wanted to listen.
But you can recover them. I mean, you can make it graded. So it's a graded SR2 rotation, to be strictly speaking. Correct? And in this case, the degree maybe the only the one moment, and you take the usual degree.
Except there is no x1 and x2. I don't know.
I mean, these variables, now they're all
So E1 and E2 are like x1 plus x2 and x1.
E2 is
Sorry.
So E1 and E2 are elementary symmetric functions.
Yeah, E1 I just. I mean, I took this representation, but actually the one I want to play with is this one. I mean, I want to see equivalent Kornoff-Rosansky GLN homology as module over this ring. I mean, of course, you can always see them as a module over this ring if you want to, but I don't need to. So I'm going to play with that one.
Yeah, but the formulas for E1 and 2 will be slightly more complicated.
Yeah, exactly. So yeah, small n, maybe I should have written. Small n is capital N. It plays the same role. Any other question? Okay, so far so good. I guess now you can relax a bit. I will still spend some time talking about the construction of the Kornoff-Rosansky homology, so if you know it, you can relax. But just to fix notation, so homology. Okay. And the way I want to think about KLN homology, if you already saw me already give a talk, is I want to discuss forms. So I will spend some time working with forms because forms are really at the heart of why you could possibly imagine that this SI2 action exists. And so I want to discuss this. So I will discuss forms. Forms and webs. Okay, let's start with webs. We already saw some webs this morning in Aristotle. So this is this trivalent graphs, which locally look like this. So as you may know, for this theorem, for the moment, I'm speaking about uncolored case. So in principle, I cannot, and I don't have to deal with A, B, and A plus B. I just have to do color 1 and 2, which encode the representative theory of UQ GL2, but it's as simple as I discussed all cases generally. So the theorem has no version for the colored case, but the statement is expected to hold. So these are trivalent graphs. So gamma will be a planar trivalent graph oriented with labels into integers, such that the local picture of the trivalent vertex is exactly this. So there's a flow condition. Okay. And as you probably know, this graph, you can use this graph to describe the representative theory of UQ GLN, which I will not recall here because I don't need it. So this is our web, these are webs, and now I need forms. These are certain two-dimensional CW complex with local P's. Which looks like this. I will do slightly different than usually. So the piece you can see is eventually just a piece of sheet with a label A. Then you may see something like this. This is A plus, sorry. This is A plus B. Here you have a facet which is A, and on the back in the facet which is B. So the diagonal reduce. So this is related to the relation that Alexei showed this morning, which is bi squared is equal to bi plus bi. So this is helpful in this picture. I want to describe them pretty carefully. I'm going to describe all pieces you can see if you use a Morse function. So my a priori in general, the CW complex is abstract. It's purely combinatorial with some rules, but you can embed it if you want to into the free space. And then if for this talk they will be embedded in the free space. Let's say embedded in the free space. And up to choosing a Morse function, I'm going to describe all small pieces that could show up. Okay, this is one of them. Then you have the usual zip and unzip that you use to describe. So this is again A, B, A plus B goes to A, B, and this is B and this is A. Okay, and then the other way around. Okay, I will not repeat the labels, I always label like A and B. There could eventually be caps and caps, and then could be saddles, usual saddle. And the other way around. Okay, and what do I forget? Oh yes, and then you have a singular vertex, which I usually draw like this. I will not draw it in a Morse function way because I'm not used to. But usually more like this. So it's a ping pong table, or it's a cone on a tetrahedra. So you have A plus B plus C, and let's say B plus C, and I'll let you fill. I mean, there's a way to fill the facet here, and here you have a singular point. And if you want to think about this piece, it's also related to the associativity. So if you see, if you think for a second, and you see this graph, let's say A, B, C, and you want to do a two-dimensional form that goes the other way, it will just create this line gonna push and cross the other one and then go the other way, and you just got this picture. You have to turn around a bit, but more or less that's something. But in this way, it's described in a Morse wave function. Okay, there's only at some point a critical point. Okay, very good.
Excuse me?
Yes.
What is meant by the labels and the...
So the labels are integers. What we want to think about forms is natural cobordism for these webs. And now the label for the webs do come from the fact that they were defined to describe proportional theory of GLN generated by exterior powers of the vector representation of GLN. So the A is just meant to be which exterior power you're playing with. And then you just go on using these forms to keep track of this. So the basic form you would like is take a trivalent graph, cross the interval. This is someone you want. And then you have to elevate a little bit to have it. Okay. What I want to describe now, or not describe, because you probably saw us too many times describing this. A couple of years ago, with Wagner, we defined a functor from the category of forms. Okay, so fix capital N, and the label of the graph and the forms now do live a priori in 0n, so this is form n, into z of x1, xn symmetric models. Actually, to be precise, it ends up in three. This functor is just sending someone here, gamma. So gamma is a closed web. And we associate Fn. Well, let's do it. Let gamma be a closed web, so Fn tilde will be something stupid, a priori, which is the home space in the form category of the empty into gamma. With scalars extended to this ring. So linear combination of forms going from the M2 into gamma. This is obviously infinite dimensional if you do nothing else. Here I was unprecise, but a priori here you're working up to isotopy. So take an isotopy for the graph, isotopy of the CW complex embedded. But I don't care that much because in a second this will be automatic. And the good thing about this naive functor is this is the functor for free. Because if you have a graph gamma 0 and a graph gamma 1 with a form bounding gamma 0 and gamma 1, this does induce automatically a linear map from gamma Fn of tilde of gamma 0 of Fn tilde of gamma 1.
So your category of forms is the objects are webs and the morphisms are forms.
Yes, exactly.
No relation for the moment.
No relation at all for the moment. So this is like, well, you can even do like rigid form, just fix the graph, fix the most, but let's do it seriously, so up to isotopy. So isotopy, so your graph can move in the plane. You don't care about.
They are abstract or embedded?
Yeah.
They're embedded yet. I mean, these are embedded.
I think he said that.
This is a symmetric monoid functor, right? So you
Yes.
think of them as abstract with respect to
Yes.
But
As you know, I'm gonna mod out, which will ruin all the questions you may ask about this because I will ignore the topology in a second somehow. Yes.
So maybe you said it, but I think the you're wrong. So it's a free module generated by this guy.
exactly, and free module over the ring with.
Over-
Sorry.
Linearization.
It's a free module generated by.
By such things.
Basis.
Yeah, yeah.
Basis.
Is this set here?
So it's a free module generated.
monad structure?
Sorry?
Monad structure
It's John Union tensor product
over
over
Rn?
Rn.
What is phi?
So what is empty?
Oh, MT. Okay.
Okay. No. No, we'll continue. Okay, so what we did with Wagner some time ago now is that we find a way to define an evaluation. So sigma is a closed form. Oh, forget something. Sorry for that. The forms we're considering have a little piece of extra data, which is on the facet could be floating p. So p is a polynomial, is a symmetric. So p symmetric polynomial in A variables. If you're familiar with Barnatons and you have one color, usually this is described as dots. But if you are more than, if it's more than one, then you have symmetric polynomials in 2, 3, 4, 5. Just be careful that these variables a priori are abstract and then have nothing to do so far with the x1 and xn that appear on the right. So what we define with Wagner is that you find a way to define something that will very, not completely recall, but very state, is that we define an evaluation which does depend on capital N, which is a certain sum of C, some coloring, of something which is, I don't know, and this a priori is a rational function on the x1 xn, and one of the first things we prove is actually this is a symmetric polynomial. In n variables. And I don't want to describe, I mean, because I know that describing this formula will take me the rest of the talk. So we just avoid to do that, but I just want to know that there is such a formula, and from this you can build Fn Fn from form or form n form. We do the same thing Rn node. But node to gamma, it does associate Fn of gamma, and this is a finite, is a free graded module over Rn. And moreover, it's not simply necessary, but its gradient dimension is something you want to, which was this TQFT. We're taking TQFT on trivalent graph, which was describing this intertwiners. If you are close, you should get a number. And the gradient dimension of this is exactly this number. Just recover it. Okay, very good. And from this, you can rebuild the Korner-Flosensky homology, which has many definitions. I don't know how many definitions there are now, but I mean, you can have it by category or matrix association or whatever you want it. But this is like a purely elementary combinatorial definition. This finite dimension, yes.
Maybe this is obvious, but what is the relation between Fn and F?
Oh, sorry. No, I forget. Good. I'm too quick. So Fn, you can see Fn of gamma is a quotient of Fn tilde of gamma by the kernel of the evaluation. So two elements or two linear combination here will be equal if closing with anything and evaluating give you the same thing. And a priori, the tricky part is that if you do that a priori, you have no reason to expect that it will be finite dimension anyway. Half part of the proof is to prove that it is, and it does exactly what you want. And then if you ask me where does this formula come from, I'm not sure I have a good answer yet to this question. Okay, so far so good. Maybe it's time I erase this theorem. So let's just do an example. Well, not really an example, just to tell you that you can obtain Covariance-Rosansky by this cube of resolution property, where you resolve each crossing either this way and the same for the negative crossing. Okay, you have two kinds of resolution. So you take a diagram, let's say I take you off because I'm lazy. You obtain something like this. And the second. So this abstractly, you can make it play in a diagrammatic or in a complex over the form category. And then you apply this functor Fn. Bring you in real algebra, meaning this is now free Rn models. And the fact that we obtain the functor Fn through what's called the universal construction, which is due to Blanchet-Gamma in the restricting to setting, is for free also that all maps that you can imagine coming in a form-like way do induce linear maps. And in particular, the map you see here is just a form like this. I mean, it's just, you go from the theta graph into, you want to go into two circles. So you just do this saddle, you glue it, and you just obtain something like this. So it's a singular saddle. And all maps in this complex are of this kind. And we do understand them well algebraically and topologically. Very good. So the status was, now we want to enrich this situation with an SL2 action. Okay. What we want to do is be able to define an SL2 action here, an SL2 action here, an SL2 action here, and so on, such that the map which is just here does not just induce a linear map, it's an SL2 map, so compatible with the action. And then you cross-finger and you hope so that you can reprove, using the old proof of the invariance, that this SL2 action is compatible with the old proof of invariance. And more or less this theorem is saying, yes, you can do that. Now, what I want to spend probably the rest of the lecture, but not completely, is telling you why you could expect, or what's the strategy to prove, to construct the SL2 action on this Fn graph gamma. Okay. Any questions? Well, the key point is, this is I wanted to recall, the key point is that we have this formula and that we build Fn this way. For instance, you may wonder, even for n equal 2, the construction we have here as n equal 2 is giving you enough homology, but somehow in a nicer way because it's functorial tricky. So this theory with forms gives you a straight functor from links into bigraded vector space of bigraded models. And you may wonder, and people have tried to build this SL2 action, for instance, in the Barn-Upper category, which is your usual setting where you play with Kovanov homology. And as to the best of our knowledge, to build this SL2 action, you need forms. Even in the n equal 2 case where you have another description using more simpler description. You may wonder also why I do care about equivariant Kovanov-Rosansky link homology, and we do care. If you remove the equivariance, then there's no action. I mean, there's no interesting action anymore. Something happens with the coefficients. Okay.
So equivariant meaning that you symmetrize a variable, or what?
No, meaning that right here. So the usual non-equivariant version would be send x1 and xn to be 0. Which is fine because this is a free model over this string, so you can tensor with the trivial representation of this algebra, and you get something, and you get just a Z module, and that's the usual graded, triple graded, or you would like to send x1 and xn to different root of unity, and you have this complete deformation, organic deformation, which is interesting because you have this concordance invariance lying inside, and somehow this theory is the equivalent. What's good about the equivalent is that it does control all of them. You can recover everything you want, if you want. I mean, I'm not saying it's easy to recover what you want, but you can, impossible. So of course, it's more complicated because computing, for instance, homology for free modules over this ring is not an easy task. Even if you put rational, you have, I mean, this is not anymore PID. I mean, even the more basic questions become more complicated once you start. So one of the easiest ways is just try to keep at least one of the variables. Like, try to keep E1.
So,
That would be the first question.
what it is in covariance fittings, these variables?
These variables in the equivalence used to be x1 and x2. So it's E1 and E2. You deform the Barnard category such that the net cutting relation, for instance, is not true. Is as a correction term, which
So
is
I'm deforming by saying that two dots are equal to E1, one dot plus E2, yeah? Okay.
so good. No, there's a very nice fact that we not prove because that's purely, but it's really why all of this is working. Okay. Before going to the key facts, so now you would like to define an action of SL2 on phones, let's say, to start with. Well, let's look to the first piece. We want to define, I mean, the more reasonable way you want to define the action locally on each piece. So this is where I spent some time describing exactly what the local pieces are. So you could try to define an action of E, F, and H by giving explicit formula. What E of this is, what E of this is, and blah, blah, blah. Okay? And this is what you do. But now if you wait for a second and say, okay, cool, let's do that. But then how do you prove it does not depend on the Morse function you decompose? And the magic is that we don't care. Because at the end of the day, we don't want Fn tilde. We want Fn. So if somehow this action you are able to define is compatible in a reasonable way with the evaluation, then the topology, that the way you build it inside, is completely captured. And you have no crazy, I mean, because otherwise you would have to describe Morse move between Morse decomposition of an embedded form into the 3 space, and this is something you surely don't want to do. So basically the ID, so the two key, so ID, so two key ID. Okay, define the action of E and H locally. First. Second, check compatibility with the evaluation. Okay, I don't want to give you all the formulas, and there's no point to do that. So I'll just give you a couple of formulas how the action looks like. So for instance, I don't know, examples. Let's say H of a cap is n minus 1. This cap. F saddle is something like E1 over 2, and this is a place I start to put constraints. Plus, I don't know. So when I don't put labels, this just means it's one color. So by this I mean just x. So just x as a polynomial in one variable corresponding to this facet. So I hope I didn't.
Close your parentheses.
That's fine.
No, not here.
No, mine. Minus 2. Something like that. I mean, you check in the paper because I'll do the crash. And for instance, E, everything, well, the point is that everything is explicit.
So you need the rationals.
Yeah, that's a good point. I would want to just say it in a second. I achieved so far. So everything I said so far for the construction of the link homology is fine over Z. And it's nice it was fine over Z. I mean, it's not, I think it's really nice that it's working over Z. But as you see now in this formula, this is not good anymore. So from now on, and let's say, let me just get E of something. Hello, E of something. This is 0. E, I can tell you what it does. E is a 0 on everything, which is topology, and it does act on this P as you would expect, using the formulas I had at the beginning. And then F do something interesting, and this theory is graded, and this form you can tell of the degree of a form, and what is H doing is just giving you back up to signs the coefficient, which is a degree. Which is exactly what's doing, if you think about it, x dx is applied to a polynomial just giving you the degree of the polynomial. So you will do the same on forms.
Is this just a guess, or is it in some way canonical, determined by some certain condition?
I mean, it's a guess because we want the second fact. We want the compatibility with the form evaluation. And from there, you are slight fixable. So we spent some time thinking about it. We put parameters a priori, and we reduce parameters. I mean, we didn't put that in the paper. So we didn't say, well, we fixed random parameters of what the action could be, and then we compute everything and check all what's happening. But in practice, this is what happened. We try to fix, to keep as much freedom as you can. And the formula which is in the paper is what remains when you put all constraints on it. But again, I mean, there's very easy things that. So, for instance, you may wonder why there's a 2 here. And if you try to think about it, this will be quickly imposed by the fact that you have a pair of points. So, if, for instance, if this kind of 2 inverts does come from the fact that you have a relation when you have a pair of points and you put a cup, it's just the identity. And this topology forces something. Yes.
This is really about a cup and
yes.
not about a disk, right?
Yeah.
So I need to know what source and target are.
Yes, exactly.
And in the saddle, you also had some sideways boundary. So is this a is this a statement about an action on morphism or 2 morphism spaces in a 2 category, or how should I think about it?
Yes. The answer is yes. I mean, we didn't do it, but you could extend it to the arc version and roll all the process until the end.
Is this action compatible with tensor product or composition of?
Yeah. I mean, then you choose your form, choose the most function, decompose, and now I give you the action on each piece, and it does act as a derivation. So it does act on the first piece plus action on the second piece plus blah 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 plus blah blah. And you just use Leibniz. I mean, just extend the action by Leibniz. But again, this a priori is that, I mean, the first thing when you define this formula, you check that you satisfy the relation. That's one of the constraints. Like you cannot choose H, F, and E completely freely, because if EF minus FE is acting on a cup, at least it should be 2 times H acting on the cup. I mean, this is something like forces you part of the parameters. Then surely at the end of the day, we don't want it to depend on the topology. So you don't check all more smooth, but you pick a certain amount of more smooth and try to say, okay, how do I define the action such that there's a slight chance that it will not depend on the topology, or I mean, meaning that it does not depend on the most function you choose at the beginning. You don't want to discuss everything because of the second point, but still you want it at the end of the day. So this is the way you choose the parameter. So we didn't choose randomly the formulas. And I didn't put there's some freedom. So there's some parameters which are free. So it's a like 2-parameter action, if you want. I should have said that this idea of having an SL2 action is not for a must. It was already appearing in the work of Wagner on triply graded, and this SL2 action also in that case can be extended to a half bit action. So you cannot just take you excite to the end, and this would be fine. It was also developed by Ben Elias and Chiu on the Zogel setting more generally. And one part of this action was used by Josh Wang when he proved that SLP over catalyst P is the same as reduced and unreduced theory. So something which was known from before for P equal 2, and this was extended, and some of these operators, or the F operator actually, plays a role in this construction. So it was around somehow. The novelty here is that we are going away from the braid closures. This is working for general diagrams and for general surfaces. Okay, so that's defines the action locally. That's a couple, and key fact. Key fact. So X, pick an element of SL2. So now you can do 2 things. You can take your element and sigma some a closed form. You can act on your form. It gives you some crazy linear combination of forms, whatever. Okay, but now you could evaluate this crazy linear combination of forms. And the key fact is that, well, which is key because we choose the formula to do that. The other thing you can do is you can take your form, evaluate. You end up in Rn, and then act with the formulas I gave at the beginning. And the output is that this is the same. You can do it either way. Sorry, someone asked me about this comment. So from now on, you replace Z of x1, xn symmetrized by k x1, xn, and 2 is invertible in K. We need 2 to be invertible.
K is a ring.
K is a ring. I mean, for some purpose, things we are interested in is for instance, what's the finite field of characteristic P. For whatever, you can take rationals, that's fine. You can use that. Okay, so the key part is this, and this is small computation. I mean, you have to know the formula, of course, but I mean, it's not such a big deal. But what you gain is that this action, you gain quite a lot of things, is that this action of X, which is defined on form, will go on Fn for free. That's one thing. But moreover, you don't have to care about the fact that you define it locally. Because the form evaluation doesn't care about the morph function. It's just evaluating the form from the combinatorial data, whatever its embedded is. So the output, so the consequence, that's it. The consequence is that the SL2 action is well defined on Fn of gamma. And I mean, meaning that it goes for the quotient is really following. If you have someone in the kernel of the evaluation, X of it will be in the kernel of the evaluation just for free because it's a derivation and just because of this formula. It's really a very nice, quick and cute computation. And what I'm hidden now is that there are some thing you have to do is find. So I had the SL2 action here and the SL2 action here, but actually SL2 is also acting here. The way I constructed it, the SL2 action is acting on any piece of form you can see everywhere. So this means that if I want to do compatibility, so if your SL2 action is not trivial on this form, it will never be a map of SL2 representation. That's not possible. Because it should act as 0 if you want this. So there's a trick which is twisting, so we can change the SL2 structure locally on Fn of gamma. Okay. So unfortunately, I don't have time to spend on that. So a priori, from what I said so far, there's a problem. This map, in particular, for instance, will never be an SL2 morphism for the action I defined on the left and the right. Let's talk about what we hope to do for.
So this means that it does not commute with the boundary map.
It does not commute with the boundary map. So you have to modify the SL2 action here. And the reason is very easy. If you pick an element here, it's a form from empty into something. Where it does go for empty into something post-composed with that. But if you want to compute the SL2, and that's the element in the target. But if you compute the SL2 action on the target, well, it does derive the first part, fine, this is what you had as a SL2 action here, but it also does derive the second part as the composition, just because the line is low. So it cannot be SL2 compatible. But there's a way to fix this, which is deforming, which is twisting. So basically, the idea is that, let me give an idea, so let's talk about something like that. And then I tell the fun you can do of this that. So let's come back to the first example. So I had an action of SL2 on the ground ring. And this is an algebra, and you can define the action on generators and extend it by Latin. But now you would like to see is just, you don't care about the algebra morphism. I mean, you don't care about the algebra structure a priori of this as a SL2 representation. So what you could do is you can define f of 1. You could change the definition of f of 1, which is typically what we do is just send f of 1 to e1. And you can check, doing so, you have a new SL2 representation, which is compatible, which is new one. And basically, what you have to do to fix this is not really much more than this. Okay, maybe I'll tell 2 minutes about topology, and then I can ask questions about more algebra techniques. So what is the fun I was saying is that you can check everything you wanted known about Kovanoff-Rosansky homology, whether or not it's compatible with SL2. So one of the theorem, which is fun, is which well, maybe it's very optimistic. So you have a very nice result that if you have not K0, so K0, and here you have a ribbon components. It has been proved in various homology settings that if, in this case, the homology theory of K0 is, this map is injective at the level of the homology theory. So it's known that Kn of K0 injects into Kn of K1. Fine. But now it's compatible with the SL2 action. Fine. But actually it's better than that, because the way they prove the injectivity is to understand what the map, a part of the map which is the other way around, which make it injective. And this map is also compatible with the SL2 action. So in other words, what you have here is that Kn, if you have a concordance, a ribbon concordance from K0 to K1, this should be a direct summand as a SL2 representation of that one, which a priori is a constraint. I mean, being a submodel is not that complicated. Being a direct summand a priori is something which may not be true always. So we hope to address this kind of question. I mean, it's hard because obviously, even if I didn't say you could guess it, all of this is pretty hard to compute. I mean, basically, we can compute 2 n torus knots, and that's basically it. So another thing which is fun is that there's an interpretation of the Rasmussen invariant, or generalized Rasmussen invariant for n bigger than 2, and you can reformulate where does it play around with the SL2 action, and it turns out that basically the Rasmussen invariant is the highest weight of a quotient representation. So you have an interpretation of this topological invariant as something coming from representation theory, which is fun. And I think I'm stopping here because I'm old.
Any questions?
What do you mean by highest weight? You just told us what category you're
Because I'm taking a quotient, which will end up. So it's known for a knot, n equal 2, it's known that the KR2 homology is torsion with action with respect to the base point. So you choose the base point. You want to reduce. And you may ask what's reducing in the equivalent case. And so you choose just the action of adding a point here. And it has been known for a while that this is, with respect to this action, there's a free part. I mean, there's only one free part. And the rest is torsion. And you look to the free part. And then you can read, I mean, it was known also in that case that the Rasmussen invariant can be seen just from the free part. And what you just notice, I mean, it's just a remark, you just notice that with the situation we define, this Rasmussen invariant is just the highest weight, plus 1, I mean, there's a slight shift, but I mean.
With the SL2 action where you had to somehow twist in the cube of resolutions,
Yes.
what is an invariant of in the end? Is it still frame-oriented links, or do you have
I mean,
theory choices?
yes. You can think about something I didn't explain carefully, but about this twisting. It's not a grading shift. It's slightly more complicated than that, but in most cases, I mean, for instance, if n equal 2, I mean, it doesn't depend on locally where it does the twist. So you have a twisting which just depends a priori on the diagram, which is painful. But you have a fix. So the quick answer is an unframed invariant. It's more naturally a framed invariant. I mean, but like most of the theory, it's just that in this setting usually costs you a bit more. I mean, in the non-category phase, it was just, okay, randomized by Rice, fine. In the usual homological time, okay, you just have to shift properly such as it's an invariant, fine. And now you have to be slightly more than that, but not that much more. And it can be fixed. So it's an unframed invariant if you want to. Yeah.
And is there a canonical choice or some coherent choice of this fix, or how much wiggle room is there?
So I think it's canonical at the end of the day because I didn't talk too much about functoriality. But you can check that the proof of invariance or the functoriality are compatible with the SL2 action. So the first bit, the first moving moves, as you know, just control the fact how much canonical is the chain complex. The homotopy type of the chain complex you associate to the link diagram, and this is completely SL2 compatible. So it doesn't have, in this sense, it doesn't depend really on your diagram and where you put the green dots. So the twist. I should have said that you can think about the modification. We think about modification. You have a diagram, and then you have some dots, which takes care of the things. But this dot can slide. It doesn't depend where it is on a knot. On a web, it's another story. But again, we have moves. We understand the move what's happening for this twisting on the web.
If you have more components.
You have one dot per component and it does slide everywhere, and that's fine. So you're thinking of this dot as a correction of the framing.
Can you extend to the deformation, which gives a spectral sequence at the basis of this Rasmussen invariant?
I would say no.
That would save a functoriality.
It's functorial as much as it can. It's really a functor for what you hope for. If it's a concordance, then it's a functor. If you take the subcategory of knots, which is not nice, and which is just knots and morphism are concordance, then it's a functor. It's a well-defined functor into SL2 operation. But if now you want topology of the surface, take a pair of points on the trefoil. The source is a trefoil, the target is addition of two trefoil, and imagine the pair of points going from one to the other. Then this guy has topology. But again, the SL2 action will be acting on the surface. So as you see, the action is pretty much non-trivial on the pair of points on the topology. So it will not be a functor on the nose. You have to modify the source or the target by twisting it properly such that it becomes a functor. So it's in the end, there's a fancy way to say it, but enriching SL2 opposition space. But I don't like this fancy way of saying it.
Last question, maybe?
Yeah, is there any UQSL2 action?
Okay, we don't know. And I'm sure we don't want, because the only way we may think about it is having a non-competitive version of this form evaluation, which is we are not able to convince people about form evaluation in a competitive setting. I cannot imagine giving talk about form evaluation in a non-competitive setting.
Have to ask question, because if you want quantum SL2 action, then you should have it on the polynomial ring as well. So you need to add a variable.
Exactly.
The calculation extends to the width action. So you would want the UQSL2 to extend to quantum width, whatever it is, which is, I think, a reasonable question as well. But people have studied quantum Virasora, but I think they're complicated.
The cost is, the worst thing is that xi's don't commute anymore, the q commutes. I cannot imagine something qualitative in this set.
Thank you, Manuel, again.